Okay, here we are, Geometry and Data, Unit 4, Investigation 6, Lesson 1. We're going to be talking about inscribed and central angles. If you take a look at the diagram at the top, an inscribed angle is one where its vertex lies on the circle, and a central angle is one whose vertex is at the center. And so we're going to be looking at angles today that where an inscribed angle and a central angle together both intercept the same arc. So if you look at the examples down below, I'm going to be using green to mark the inscribed angles, and blue to mark the central angles, and orange to mark the arc that they share. So let's look at number 1 down below. In each figure, we need to name the inscribed angle, the central angle that intercepts the same arc, and then classify the intercepted arc as major, minor, or semicircle. For the first one, the inscribed angle is angle CFB. And the central angle is a little tricky here. It's actually angle CEB. And that's a straight angle. And that leaves me the intercepted arc that comes around here from C to B. And what we call that arc is a semicircle. In the next one, the inscribed angle. So I'm looking for two angles, an inscribed and a central angle that both intercept the same arc. So if I look, I see that arc AD is intercepted by the inscribed angle AHD and the central angle AGD. So the inscribed angle was AHD because its vertex is on the outside of the circle, or on the circle itself, the circumference, and the central angle is AGD. And AD is what we would call a minor arc because it's less than 180 degrees. And the last one is what we would call a major arc because it's more than 180 degrees. And it's intercepted by the inscribed angle MLJ. And the central angle MKI. And they're talking, this little circle here means they're talking about that part of the angle, not the acute part of the angle, but they call this the reflex angle. So we're going to call that MKI. And this is a major arc. So we can do a little investigating to see if we can figure out the relationships between an inscribed angle and the central angle that intercepts that same arc. So take a look at page 95. And in this picture you'll see what I did was I marked out using the same colors the central angle CDA and the inscribed angle CEA, and they're the arc that they both intercept, arc AC. And what this activity is going to have you do is use a protractor to measure the inscribed and central angle for the next 4 or 5 examples and see if you can see the relationship. So at this time, please pause the video and use a protractor to measure all the way up through example E. Okay, hopefully you took some time to do that. If you take a look at example A, we found the central angle was 40 and the inscribed angle was 20. For example B, I had 60 and 30. Example C, 120 and 60. Feel free to pause this video at any time or rewind it if you need to watch again. Example D, And lastly, example 8. Hopefully by now you're starting to see the pattern that the inscribed angle is always half of the measure of the central angle that intercepts the same arc. So let's write that down below for number 2. What pattern did we notice? The measure of the inscribed angle is 1/2 of the measure of the central angle that intercepts the same arc. And so that would be the same as the conjecture of what we're saying below. Alright, so let's take a look at page 98. Here's some practice problems for us. What might help is if you continue to mark them up using colors so that you can see the two angles we're talking about. Once you get better at it and you can start picking the diagrams out, you don't need to keep doing that. But if it helps you visualize and see that, that's what makes it easier. So they're telling me angle D is 25 degrees. And so what I know is if the inscribed angle is half of the central angle, then the central angle will always be double of the inscribed angle. So in this case, I know that x equals 50 degrees because it's double 25. Okay. Letter B. Each one of these is a little different, and the diagrams will start getting a little trickier and trickier. For B, they're telling me angle D is 15 degrees. And to be honest, you don't even need to know anything about inscribed angles to answer this. You might remember that this triangle, ACD, is an isosceles triangle because it's formed with the radii of the same circle. And those are congruent, so base angles are congruent. You could have, if you wanted to, looked at the 15-degree angle as an inscribed angle. And you may have realized that the central angle, BAC, would have been double that. So this one would have been 30. Then I could have used what I know about an exterior angle of a triangle is equal to the sum of the remote interior angles. So 30 equals 15 plus something. So x has to be 15. Or you could find that this obtuse angle in the triangle is supplementary because these are a linear pair. So this angle would have had to have been 150 and then subtracted 150 and 15 from 180. You still would find that x is 15. C, unless I'm losing my mind, I think there's a mistake. I think we're looking for this angle up here. And so if you look at the intercepted arc, they start to get a little harder to find as the diagrams get more complicated, but once you get practicing with them, it'll get easier. So in this case, I'm looking at these two angles. They're telling me that BAC is 90 degrees, so therefore x would be, because it's the interior angle here, it would be half of the central angle. So x would be 45. Okay. Part D, measure of angle B is 32 degrees. And I know that that intercepts, angle B intercepts this arc. So the central angle A that intercepts the same arc would be 64. And I know that this is an isosceles triangle because these are radii from the same circle. So from here, I would just subtract 64 from 180 and then divide it in 2 to find the two base angles that will be congruent, because the base angles in an isosceles triangle are congruent. So I'm going to let you keep going there with practicing and finishing to solve that. And I just want to talk to you about a couple other quick things that have to do with these same ideas. And the first idea to talk about is Thales' theorem. You can read a little bit about him at the top of page 100. If you take a look down at the bottom of the page, though, the big idea with Thales' theorem is that if we inscribe, if an inscribed angle intercepts a semicircle, then its angle will always be a right angle. And that makes sense because a semicircle has 180 degrees and the inscribed angle would be half of that, would be 90 degrees. So that's how we get there. But we can use that information to solve even more complicated problems, because not only do we know that this angle is 90 degrees, but now in doing so, with the diameter would end up being the hypotenuse of a right triangle formed. So now it opens up even more options for solving more and more difficult problems. If you take a look at page 101, you'll see that we asked you to draw a picture of the scenario of Thales' theorem where you have a inscribed angle intercepting a semicircle. And we know the intercepted arc is 180 degrees. So that's what's given. We know that we're trying to prove that the inscribed angle would be 90 degrees. So since the measure of an inscribed angle is half of the measure of the central angle with the same arc, it must be 90 degrees. And there's a few examples for you to try with these as well. For example, number 4 says KT is the diameter of circle O, CT is 5, CK is 12, and they want us to find CO. So this is what they're looking for right here. Now what I know is because this inscribed angle intercepts a semicircle, that this is a right angle, which means triangle KCT is a right triangle. And it's not just any right triangle, it's a special right triangle. It's a Pythagorean triple, 5, 12. So that means the diameter of this circle must be 13. Which tells me that the radius is 6.5. And since radii of the same circle are always congruent, the solution I'm looking for is 6.5 centimeters. There's some more examples for you to try on page 104, 105. The last thing I want to mention briefly is something called cyclic quadrilaterals. And this is on page 107 in your book. And this is basically a cyclic quadrilateral is if we join 4 points around a circle consecutively by chords. And the big idea with this is, if you take a look, let's say for example I look at angle A here, and that intercepts this arc DB. And if I look at angle C, which is across from angle A, that intercepts this arc up here. And what you'll notice if you start to look at all of these is if you look at the intercepted arc of any of the opposite angles in the quadrilaterals, they will always, when you put the two arcs together, it'll always make the whole circle. Well, since the inscribed angles are always half of the measure of the intercepted arc, then I can assume that the sum of the measures of opposite angles in a quadrilateral, a cyclic quadrilateral, will be supplementary, and they will add to 180 degrees. So you can look at a couple of these just for example, so you're getting the hang of it. But basically, like if I looked at this angle C, DCB, that gives me this arc. And if I look at the angle opposite of that, I have angle DAB, and that intercepted arc is here. So between the pink arc and the green arc, I've covered the entire circle. And the measure of the inscribed angle is always half of the intercepted arc. So since the whole arc is 360, the sum of the opposite